Hello, good morning, everybody. My name is Thomas Mueller. I'm the Director of Applications Development for the AFM business at Bruker. I'd like to welcome you to this installment of our Bruker AFM webinar series today. The presentation here is called AFM for Solar Fuels Research, Nanoscale Charge Transport in Water Splitting Photoanodes. It will be presented today jointly by Drs. Francesca Toma and Johanna Eichhorn from Lawrence Berkeley National Lab. Before I introduce the speakers, I'd like to make a few quick logistical comments, as well as comments about this webinar series. First, we encourage your participation during the webinar. If you have a question, please type it into the questions dialog box on your screen. We'll accumulate these questions through the presentation, group them together, and then answer them at the end of the prepared remarks. Quite often, we have more questions than we can answer in the session, and in those cases, we'll be sure to follow up by email. Also, if you'd like to review the presentation afterwards or pass it to a colleague, the webinar will be posted online within a week in the webinar section of the Bruker AFM webpage. As a follow-up to this presentation, you'll also be receiving an email with this link. Finally, when you exit the webinar software, you'll be asked to take a brief survey. We'd very much appreciate if you take the time to complete this, as it helps us pick the topics that are most interesting to you and generally make this series better. Now, let me say a few words about this webinar series. Today we have one of our webinars in the series of webinars for energy research. This is an overarching series we have of webinars that cover photovoltaics, lithium-ion batteries, as well as solar fuels and the fuel cells. Recently on lithium-ion batteries alone, we've had 4 webinars focusing on anode and cathode mapping and our AFM-based SCCM capabilities. We did some of them jointly with researchers from General Motors as well as the Sheldon Group from Brown. Within that overarching series of AFM for energy research, we have our current series of solar fuels research, where here too we've had a number of webinars with our customers, with researchers. They included nanoelectrics at electrified solid-liquid interfaces with the Bruker Group from Oregon. Most recently, Professor Fan from the Chinese Academy of Sciences, and today, Dr. Francesca Toma and her team at Lawrence Berkeley Lab. Now, all the experimental data you see in these webinars was acquired using our Dimension Icon and FastScan platform, which is one with an open motorized stage, and that's used often in this work for electrochemical control, environmental control, photoconductive, or photoelectrochemical studies. As far as AFM modes, you see sometimes feature the peak force tapping, as it's amenable particularly for looking at very fragile and loose adsorbates, as well as you'll see in some cases our nanoelectrode probe featured that lets you do sub-100 nanometer local electrochemical mapping. You've also seen recently in our webinars our data cube modes, where we get electrical spectra at every pixel. That being said, about some of the capabilities you see in these webinars, speaking about our co-presenters, really all of them in this energy research series have had a number of high-impact publications recently. On this slide here, I'm highlighting in yellow some of the recent high-impact publications by Drs. Toma and Eichhorn. They're Nature Communications, Nature Energy, as well as ACS Applied Materials Interfaces publications. Let me introduce our 2 speakers more properly at this point. Dr. Francesca Toma is a principal investigator and staff scientist at the Joint Center for Artificial Photosynthesis, Lawrence Berkeley National Lab. Her specific research interests lie in the synthesis, characterization, and integration of light absorber catalyst assemblies, and on the development of in situ and in operando microscopy techniques to study energy-efficient systems. Dr. Johanna Eichhorn is a postdoctoral fellow in the Chemical Sciences Division at Lawrence Berkeley Lab. She received her PhD in physics from Technische Universität München, Germany, and her current research interest is to understand interfacial charge transport in photoanode materials for solar water splitting. So with this, let's get started with the real presentation here, and let me turn it over now to Dr. Francesca Toma.
Today I'm going to introduce a little bit the motivation of our research here at Lawrence Berkeley National Lab. Our research group is focused on the synthesis and characterization of materials for water splitting and carbon dioxide reduction. So if we look at numbers, and specifically if we look at the vital signs of the planet that are published on the climate.nasa.gov website, we can see how recently the climate change has touched alarming levels. Specifically, we can see that we have higher parts per million of carbon dioxides that have been increasing in the past 650,000 years. We have highest numbers of years, of following years with higher temperature. So we're increasing the temperature of about 1.8 degrees Fahrenheit since 1880. And this has caused the Arctic ice to raise its minimum levels, as well as the decrease of ice sheet. And in addition to that, all of this caused the increase of the sea level. So continuing on this line, one can also look at the United Nations Sustainable Development Goals number 7, which is indeed on affordable and clean energy. So the United Nations recognize energy as the dominant contributor to climate change, and in fact it accounts for 60% of the total greenhouse gases emission. So as targets, the United Nations has by 2030 to increase the share of renewable energy in the global energy mix, but also to enhance the international cooperation to facilitate access to clean energy. So the concept of utilizing renewable and clean energy is actually quite old, and one of the first scientific article on the topic was published back in 1912 on a science paper by an Italian chemist, Giacomo Chamichan, who was also known as one of the father of photoelectrochemistry or photochemistry. And back then, Giacomo Chamichan was wondering whether it would not be advantageous to make a better use of radiant energy. And if we look at numbers even nowadays, and we look back at 2008, the global energy need was about 15 terawatts, and the predicted one by 2050 is going to be 60 terawatts. However, we should consider that the sun is giving us a flux of 120,000 terawatts, which is 4 orders of magnitudes what we currently need. So looking at nature, if we want to make a better use of radiant energy, we can do as nature does, so natural photosynthesis. We take water, carbon dioxide, and sunlight, and we can convert radiant energy in chemical energy. So specifically, we could translate this process and do artificial photosynthesis and do specifically splitting of water into hydrogen and oxygen. So hydrogen would be our energy dense molecule, and oxygen would be our byproduct in a totally clean approach. However, to split water electrochemically, we need a thermodynamic potential of 123 volts, which becomes 1.7 if we consider the complex kinetics that are related to the oxygen and hydrogen production semi-reactions. So if we want to get this 1.7 volt, we could utilize a tandem approach in which we have two semiconductors in tandem that are absorbing the visible light and then are providing a sufficient photovoltage to give us this 1.7 volt that will enable us for autonomous water splitting. In addition to that, we can define other targets, like trying to do this reaction with a solar to hydrogen efficiency higher than 10% and with the durable and robust device. So at the Joint Center for Artificial Photosynthesis, we recently showed that this is possible, and now I'm going to show you a video which demonstrates how you can use a 3-5 semiconductor triple junction, shine light on it, and develop hydrogen. So the video is starting now. We switch on the light, and then you see those bubbles that are hydrogen bubbles produced at the semiconductor surface, which is interfaced with a catalyst. So this looks quite simple. However, we need to consider that to realize this integrated solar fuel devices, we actually need several components that have to be all integrated together, and charge generation and separation needs to be orchestrated in a way in which the reaction can be catalyzed. So specifically in our device, on the outer layers, we need catalysts, and we have oxygen evolving reaction catalyst at the photoanode side, and then we have an hydrogen evolving catalyst at the photocathode site. Then we need light absorbers, and specifically we need a photoanode, which is able to catalyze oxidation. It's an N-type material, and it will be interfaced with the oxygen evolving reaction catalyst. And then on the other side of the cell, we need a photocathode, which is going to be a P-type material, and is going to catalyze the reaction, and it's going to be interfaced with the hydrogen evolving catalyst. And then we in fact need a lot of interfaces and contacts that are able to connect all these layers and ensure the charge directionality. So the topic of the seminar for today, it's going to be focused on light absorbers, and we are going to talk about how the light absorbers are involved in this reaction and how we characterize them. So tying back to the energetics of the reaction and the Venn diagram, we see here a schematic that illustrates how the energies of the different layers for the photocathode and the photoanode should be aligned. So without any catalyst on the outer layer, now we're just focusing on the light absorbers. So on the right hand side, we have the photoanode. Upon light illumination, we'll have a charge generation and separation. And on the right-hand side here, we see the interface with the electrolyte. The hose will go and oxidize water, and we have an upward band bending in this case. At the photocathode side, instead, we have a P-type material with downward band bending. The process is the same. We absorb light, we generate charges, and the electrons will travel downhill and will reduce water to hydrogen. So again, this reaction is a high energy demanding reaction because we need to remove 4 protons from water, 4 electrons to generate oxygen. And then we need to generate hydrogen as well. So we need this 1.7 volt, and thus we need to select our semiconductors in a way in which we get this photovoltage of 1.7 volt. So for example, we can use a photoanode that gives us about 1.1 volt, and Johanna is specifically going to talk about this type of photoanode. And then we can use a photocathode, let's say silicon, which gives us a photovoltage of about 0.6 volts, which altogether would allow us to carry out the water splitting reaction. So the ideal tandem device shows efficient charge generation and separation, and transform these charges in in chemical reaction and in chemical bonds. However, we can have device limitations that are due to bulk properties, but also to the inefficient charge separation at the semiconductor electrolyte junction. So the understanding of the bulk properties, but also of the surface interaction with absorbates in light-absorbing material becomes really important in order to develop novel materials that can efficiently carry out water splitting. Now I'm going to let Johanna continue from this point, and she will show more specific results on how we do this understanding and how we provide this characterization.
Thank you, Francesca, for the introduction. And in my part of the talk, I will specifically focus on photoanode material, specifically on bismuth vanadate. Bismuth vanadate is a promising photoanode material due to the bandgap of 2.5 eV, which is small enough to absorb visible light. It has a favorable band alignment with the water oxidation potential, long photocarrier lifetimes, and it can generate a photovoltage larger than 1 volt. However, the performance of BIVO is limited by its poor maturity carrier transport properties, but also by local variations in the morphology or the chemical composition. For example, in polycrystalline BIVO films, the structure is dominated by grains, and thus in this electrodes, the performance is usually can be dominated by the grains, grain boundaries, or crystal facets. However, usually used photoelectrochemical measurements use large-scale electrodes, which don't provide any information about these local variations in the performance. Therefore, a finer resolution is needed to resolve the correlation between these topography changes and on the performance of the device. Identifying these correlations will enable to design and engineer new photoelectrode materials with higher performance and efficiency. One powerful tool in this context is Photoconductive AFM, which enables to identify variations at the nanoscale. We specifically used the Bruker Dimension Icon, and we realized photoconductive AFM there by leveraging the open design of this instrument. We implemented a home-built backside illumination setup. Backside illumination has the advantage for BIVO films that the charge carriers are generated closer to the FTO back contact, and the electrons can effectively extracted by the FTO electrode. Photoconductive AFM base uses a conductive probe and an additional light source for illumination. Generally, these measurements can be performed in 2 different modes. One is the so-called current mapping mode, where the cantilever is scanned across the surface and a constant bias is applied to the FTO back contact. This kind of measurements enables to correlate distinct topographic features to its photoconductivity. Furthermore, it allows to perform IV-spectroscopy. Thereby, the cantilever is kept as a fixed position and the voltage is ramped. This kind of measurements provide insights into the underlying charge transport in the BIVO films. Furthermore, this technique has the advantage compared to standard macroscopic probe measurements, which use a large-scale top electrode that only 10 nanometer square of the samples are covered by our probe. That means the surface of our material is exposed to the surrounding environment, which makes it highly comfortable for in situ characterizations. This is especially interesting for photoelectrochemical materials, which are usually investigated at a solid-liquid interface. And here we can replace the solid-liquid interface by a gas-phase interface, which is less complicated, and it's a good first test to investigate selectively the molecular absorption on the surface of the material and the effect of the charge transport. Furthermore, it has the advantage that we can locally record IV measurements, which is especially important for polycrystalline films like BIVO. In the following, I will first show that we use current mapping to resolve spatial correlation between the topography and the photoconductivity. And in the second part, I will focus on charge transport measurements by IV spectroscopy. So we recorded the current maps with the platinum iridium coated probes, and we applied a potential of 1.75 volts. We conducted these measurements in the dark and under illumination. In the dark, we see almost no current, except of some distinct bright features with higher conductivity. These small features we assign to shunts between our conducted cantilever and the FTO back contact. In this context, TEM cross-section measurements reveals pinholes in our BIVO film, which could act as a starting point for the shunts we observe. When we use below bandgap illumination, we almost see no change in the current. However, when we illuminate the sample with above bandgap illumination, we see a clear photoresponse. Accordingly, we can assign the photoresponse to generation of electrons and holes across the bandgap. If we have a look at the current map, we clearly see variations in the photocurrent between different grains. However, when we determine the average current per grain, we cannot resolve any correlation between the grain size and the average photocurrent. In the following, we will analyze the distribution of the photocurrent across the sample to determine the correlation between specific features in the topography with the photoconductivity. For this, we define three different regions: the grain boundaries, facet planes, and facet boundaries. We use the line profile to define these different regions. Grain boundaries are defined as concave valleys between single grains, and facet planes are defined as regions with vanishing curvature, and the intersection between different facet planes we define as facet boundaries, which are characterized by a convex curvature. In the following, we use these three masks to extract the current distribution in the photocurrent map in these three regions. In the histogram, we clearly see that we observe an increased current for the facet boundaries. To investigate the dependence on the cantilever coating, we performed the same measurements with a gold-coated probe at the same sample position. If we look at the histogram, we see a current distribution which is similar in all three different regions. So this pronounced dependence of the cantilever coating on the photoconductive contrast shows us that there is a variation in the interface energetics at the contact between the probe and the BIVO thin film. Generally, the contact between the BIVO and the probe depends on the energy barrier at this contact, contact, but also on the applied force. The energy barrier can be estimated by the difference between the work function of the probe coating and the electron affinity of the BIVO thin film. To get an idea about the barrier at the interface, we performed Kelvin probe measurements using gold and platinum iridium coated cantilevers on a freshly cleaved HOPG. And we find out that the work function between these materials slightly differs by 0.1 eV. This change in the work function results in a change in the energy barrier, which might relate it to the increased current we observe in the photocurrent map conducted with the gold-coated cantilever. Furthermore, the contact also depends on the applied force. To get an idea about the dependence, we recorded photocurrent maps for increasing applied forces, and then we extracted the average current of each image. Below in the diagrams you see the average current versus the applied force. For both cantilever coatings we see a clear dependence on the applied force, which is more pronounced for the platinum iridium coated cantilevers. For the gold cantilever, we see that already really low applied forces result in a good electric contact. However, if we use really high forces, we can destroy our material. Hopefully with that, I showed you that photoconductive AFM is a powerful tool to investigate heterogeneities in the functional properties of photoelectrochemical materials. And I would like to emphasize the importance of good sample probe contacts for reliable photocurrent measurements. In the following, so these measurements allow to correlate features with its photoconductivity, but they don't provide any information about the underlying charge transport. To identify the underlying charge transport, we recorded IV-spectroscopy in nitrogen atmosphere, and in the following we also investigated the influence of surface isobars on the charge transport mechanism. IV curves were recorded on top of a single grain, and they can be performed in the dark and under illumination. Under illumination, we see a clear photoresponse in the positive bias regime. The positive bias regime is in agreement with the operation conditions in the photoelectrochemical cell. The electrons are extracted by the FTO back contact, and the electrons go to the surface where they can take part at the reaction. Therefore, we will focus on the positive bias regime in the following. The IV characteristic can be best described by a linear correlation in a log-log plot, which corresponds to a power law dependence. In the following, we will run temperature-dependent IV curves to determine the underlying charge transport mechanism in BIVO thin films. So we recorded IV curves for increasing temperature starting at 25 degrees C, and we increased it to 50 degrees C. We observe an increase in the maximum current, but also we observe a change in the slope of our IV curves. Furthermore, we analyzed our data in the high bias regime, and we fitted a power law dependence. When we extrapolate these fits to a higher voltages, we observe that these solid lines intersect at a characteristic voltage, the so-called crossover voltage. So this fact that we observe a power law dependence in combination with the crossover voltage shows us that we have space charge limited transport in BIVO films. In this space charge limited transport model, a slope of 2 describes the charge transport in ideal trap-free materials, and a modification of this power law exponent is observed in the presence of trap state. For BIVO, we observe a change from 5.9 to 4.3, which indicates a space charge limited transport in the presence of trap states. In this kind of model, the power law exponent correlates to the characteristic trap energy, and which can be calculated, and in case of BIVO at room temperature it's about 0.1 eV, which indicates shallow defect states in BIVO. For increased temperature we get some trap state filling and a reduction in the characteristic trap state energy. Furthermore, we can use the characteristic crossover voltage to calculate the effective trap state density in this material, which is 5.6 times 10 to the power of 18. So in the following, we would like to investigate the influence of surface adsobars on this charge transport mechanism. For this, we recorded IV curves in oxygen-rich and humid environment. If we record the IV curves for increasing oxygen, we started about 0 oxygen and increased it to 21%. We see a reduction in the maximum current by 1 order of magnitude and an increase in the power law exponent, which indicates a reduced trap state filling in the BIVO film. This can be explained that oxygen can absorb on the BIVO surface by trapping electrons from the BIVO and the formation of O2- on the surface. The trapping of electrons by the oxygen reduced the free carrier concentration in the BIVO, which in turn reduced the trap filling within the BIVO film, which results in a stronger effect of trap states on the charge transport mechanism, which is reflected by the increase in the power law exponent. We performed similar experiments in humid environment. Interestingly, we observed the opposite behavior. We see an increase in the maximum current and we see a reduction in the power law exponent. In this context, a theoretical calculation shows that at room temperature, oxygen absorbs on the surface molecularly. So that means a dipole layer can be formed. This calculation shows that oxygen prefers to absorb close to the BIVO film and the hydrogen points away from the surface, which results in a dipole layer with a negative polarization towards the surface and a positive polarization pointing away from the surface. Furthermore, this calculation shows that oxygen and water prefer to absorb on the same binding sites in the presence of trap states. Therefore, absorption of oxygen can trigger the release of residual oxygen from the surface. Desorption from oxygen will release trapped electrons, which can fill up the existing trap stage, which is in agreement with the observed reduction in the power law exponent. In the following, we will use this sensitivity of the IV curve measurements to determine the change in the trap state density when we change the environment from nitrogen to oxygen. Therefore, we performed temperature-dependent IV curve measurements. We see again an reduction in the power law exponent, which goes closer to 2. And for the extrapolated fits, we observe the intersection at the characteristic crossover voltage. However, if we compare nitrogen and oxygen, we see a clear shift for the crossover voltage, which can be translated into a change of the effective trap density to be reduced by 40% when we change it from oxygen to nitrogen. In summary, I showed you that the charge transport in BIVO is space charge limited in the presence of trap states, that chemisorption of oxygen can act as shallow defect trap states in BIVO. Water only influences the charge transport indirectly by replacing residual oxygen on the surface, and changing the environment from oxygen to nitrogen reduces the trap state density by 40%. With that, I would like to thank you for your attention, my cooperation partners for their support, and the LDRD funding program at LBNL for support. I'm happy to take any questions.
Well, thank you very much also from my side, and thanks Johanna and Francesca for this very interesting presentation. I see we have a few questions already. To any in the audience, if you would like to ask a question, please don't hesitate to submit it in the questions dialog box. We do have a few minutes to answer them. Let's see, let me have a quick look here. So one question was, your work clearly depended on these reproducible and sort of artifact-free measurements, and you talked a bit about that. Could you say more about how to get reproducible measurements free of artifacts in your photoconductivity study?
So let me go back to the slides where I show the force dependence. So as you see from the force dependence, gold already makes a much better contact at low forces, which is definitely better for the measurements at BIVO. With BIVO, we observed that if we use too high forces, we can destroy our materials. So that means we have to find the balance between a force which is high enough to establish a good electric contact, but also not to damage our material. And for BIVO, we optimized our measurement parameters. We did some correlation plots between the height, the adhesion force, and we don't observe any correlation. This indicates us that our measurements are artifact-free.
Okay, thank you very much. Another question, since you have this metal probe on a semiconductor, you have this metal semiconductor interface, shouldn't there be a Schottky contact and rectifying IV curve? But it seems that's not what you're seeing. Could you explain that?
Sure. That's a pretty good question. I have an additional slide for this. So what we observe when we use the nanoscale probe is that our IV curve look almost symmetrically. What is, as you mentioned, is not expected for a classic metal semiconductor contact. However, we performed similar measurements with the probe station, and for this we clearly see the expected rectifying behavior. So we can assign the observed deviation from the classic rectifying behavior to the formation of a nanoscale Schottky contact. The nano-Schottky contact depletes the BIVO at the or reduce the depletion region at the surface, and with that it increased the tunneling probability, which in turn leads to an increased current in the reverse bias regime, and that's exactly what we observe in our measurements. So that's always something we have to have in mind when we perform photoconductive AFM measurements, that we might have the formation of a nanoscale Schottky contact at the surface, which can lead to that changes in the IV curves.
Okay, yeah. Thank you very much for that clarification. Now you alluded to the influence of water, and that sort of goes in an interesting direction in that ultimately maybe it would be very interesting to see what does this measurement look like in situ, in liquid, would it be possible to make these measurements in liquid or even under a photoelectrochemical control?
So Francesca published, I think in 2016, a paper about the electrochemical measurements of BIVO using the Bruker electrochemical cell. With BIVO, we are facing the challenge that BIVO is not stable under operation condition. And what Francesca observed in her measurements is that the grains shrink and the material gets dissolved in the electrolyte. So this fact makes it really challenging to perform measurements on BIVO under operation conditions.
Okay. That's too bad. It'd be interesting to see if there's a way to do that. Another question we had along different lines. Since you are interested in the IV curves and the behavior on different parts of a grain, have you, by any chance, have you tried the data cube mode that I mentioned in the introduction, where you'd get a lot of IV curves?
Unfortunately not. So we kind of found a way around it by just recording current maps at different potentials, but unfortunately we don't have access to the data cube model right now. But it definitely would be really interesting to use this kind of module for that kind of measurements.
Okay, thank you. Yeah, you mentioned environmental control with different levels of water and oxygen. You didn't do that in the glove box though, or how did you control the environment?
No, we did not. So what we did is we used the fume hood. We flashed the whole basically the whole AFM hood with nitrogen or oxygen, and we set up an environmental control by ourselves. We had some mass flow controller to control the flow in rate, and we had some oxygen and humidity sensors inside to read out constantly our level of oxygen and humidity in the hood. However, this is why we were kind of limited with the humidity level we could use for our measurements. Since we cannot go higher than 50% of humidity, otherwise there's a chance that we will damage our scan head.
Yeah. Now you mentioned that that BIVO changes morphology a lot in the electrochemical environment. But in principle, do you see your technique as being possible in liquid, maybe under either different conditions or for a different sample that is more stable in liquid?
So one possibility what we could do with the BIVO is using, for example, the scanning electrochemical microscopy module and just put BIVO in an electrolyte, and then we can also measure IV curve, or we can do like Nellis presented 2 months ago. We could potentially do something like this potential sensing. But that's always something that we have to do maybe in the dark for the beginning, because in the dark the dissolution of the BIVO is significantly reduced, so doing such measurements in the dark would be already a good starting point.
Okay. Thank you very much. We are sort of at the end of our time. I want to thank again our speakers, Dr. Johanna Eichhorn and Francesca Toma, and thank all the audience for joining us today. We'll have this webinar available for download, and you'll receive a link for that. And for the remaining questions, we will collect them and answer them by email and follow up with you. Thank you. Bye-bye.
Thank you.